So in this section, we'll be covering the final part of reaction mechanism. So the first part to introduce is actually the Boltzmann distribution graph. This is a distribution graph based on probability, which actually depicts the fraction of molecules with specific energy. So say, for example, at energy E0, we actually have a specific fraction that percentage of molecules with the energy E0, and in this case, maybe perhaps is 20%. Then similarly, at another energy E1, there will also be 20% of the molecules which have energy level E1. Therefore, when you actually total up the area under this graph, it must actually give you 100%. If you decide to plot the graph as, if the y-axis of the graph is plotted as percentage of molecules, and the area under the graph will be equal to 1 if the y-axis is plotted as fraction. Now we'll take a look at what happens when the temperature increases. Okay, when the temperature increases, it's important to take note of the peak. The peak represents the maximum percentage of molecules with a specific energy level. And in this case, when the temperature increases, in fact, the peak actually drops and it moves actually sideways towards the right. So as the temperature increases for another graph, you will actually go this way. So let us explain. So the reason for that is that when the temperature increases, all the molecules which are actually of low energy, all right, they have low energy because this part here, the energy level is lower. All this with lower energy is now being promoted to the molecules here, which have higher energy. The reason why we can conclude that is that one has to bear in mind that the area under this graph and the area under the graph when the temperature is increased must actually be equal. So as you can observe down here, this is the common pool of molecules which still have the same amount of energy. So the only change is that the molecules which has lower energy level is now being promoted to higher energy. Hence, if you are now to look at the impact of raising 10 degrees Celsius. So when you raise 10 degrees Celsius for a specific reaction, on assumption that in this reaction, this is actually the activation energy, what we can witness is that in actual fact, we actually double. So when the temperature is T1, this is the only number of molecules that have energy greater than activation energy. However, when you raise the temperature by 10 degrees Celsius, you actually double the area, which means you double the number of molecules which have energy greater than activation energy. And that helps to explain why for every 10 degrees rise in temperature, we actually manage to double the reaction rate. The next part, Boltzmann distribution, can also be used to explain catalysts. In this case, by looking at the Boltzmann distribution at a specific temperature, if we were to use catalyst, the activation energy would be decreased to E star. Therefore, because of that, these molecules which previously does not have energy greater than activation energy cannot bring about effective collisions. Now they could, in the presence of the catalyst. We're now going to discuss homogeneous and heterogeneous catalysts. In the case of homogeneous catalysts, the catalyst used has the same state as a reactant. So in this case, the catalyst used is Fe3+. Fe3+ managed to actually oxidize I- to form Fe2+. And then in the process, Fe2+ then get oxidized by your S2O8 to form your Fe3+. And that's how Fe3+ is actually being regenerated. So in this reaction, we'll see that in the presence of the catalyst, actually you will have two harms, but more importantly, the activation energy for the first harm has been reduced relative to when Fe3+ is not available to perform as a catalyst. The next question to ask is that, so can Fe2+ catalyze the reaction? The answer is yes, because if you decide to use Fe2+ first, then what happened? Fe2+ will then react with S2O8 first. Then the 3+ that's generated will then react with I- to regenerate your Fe2+. In conclusion, when Fe2+ is the catalyst, Fe3+ is the intermediate, and vice versa. If Fe3+ is the catalyst, Fe2+ is an intermediate. In the next example that we have, we're looking at heterogeneous catalysts. In the case of heterogeneous catalysts, the catalyst is typically a transition metal, which is actually a solid. Transition metals, which has partially filled 3d orbitals, allows them to interact with reactant molecules to allow them to establish temporary bonds with the transition metals. We describe that with the term XOR. Take note that XOR is actually AD, not AB. In the process of actually forming temporary bonds, it weakens the covalent bonds within the molecules, thereby lowering the activation energy. And thereafter, the reactant molecules could actually react with each other to form the product molecule, and desorption occur, and the product molecule is allowed to leave the catalytic surface. So examples of such reactions includes the formation of ammonia when nitrogen reacts with hydrogen gas. Finally, we'll look at autocatalysis. In this case, when manganate reacts with ethane diorite, Mn2 plus is an autocatalyst, which is the reason why initially the rate of reaction is pretty slow, as you can observe based on the gradient of this graph. And subsequently, the gradient of the graph becomes steeper, which means the reaction rate increases. So the reaction rate increases primarily because once the reaction kick off, you will find that your Mn2 plus that's generated becomes an autocatalyst and help to catalyze the reaction. And we want to add that why initially the reaction rate is slow is because MnO4 minus and C2O4 2 minus are both negatively charged. If they are negatively charged, they repel each other, so the activation energy will be high. Once you have Mn2 plus can take the role of reacting with one of them, produce maybe perhaps another manganese with a different oxidation state but still positively charged, that actually thereafter reacts with your manganate. Finally, the reason why the reaction rate will hot to a zero is due to the fact that either manganate or ethane diorite has been used up.